what they want us to do is, for each index, find out what is the operation is going to take us to move all the balls. Here the balls are represented by 1. So here at index 2, 4 and 5 we have got one ball each, and we need to move these balls to these all of these indexes, all of them, and then find what is the minimum number of operations required. So in this case, when we have index 0, we see that it's going to take us 11 operations. How so? We'll have to move this ball from this index to this index for 2 units, from this index to this index for 4 units, and then from this index to this index for 5 units. So 5 plus 2 7, 7 plus 4 11. The same thing is happening for this index as well. We see the balls from here, so if we are moving 1 unit here, and then 1 2 3 unit here, and then 1 2 3 4 unit here. So we have 4 3 7 plus 1 8, so in total of 8. For this unit, if for this index we see a ball is already here, so now we will have to effectively move just 2 balls. So for that, our solution becomes 2 units this distance, and then 1 2 3, total of 3 units here. So this becomes 5 right here. I'm gonna write the answer here. So 11, 8 and 5 as of now. Moving on to the second index, the third index basically. So we see we have balls on the left and the right. So the right one moves in, so we'll have 1 unit movement here, 1 unit, and then 1 unit here for this ball, and then 2 unit here. So a total of 1 plus 1 plus 2, which is 4. So 4 units for this one. For the fourth index, again we see 1 ball here already present, so effectively we are moving 2 balls. So and those are this 1 unit here movement and this 2 unit here. So 1 plus 2 gives us 3. So 3 for this one, and for the last index again this 1 ball is already here, so a total of just 1 movement here, and then 1 2 3, 1 plus 3, which gives us 4. So in the end 4 movements total. So this is how the problem is. This is what they want us to do. They to find us the effective operations we are gonna do. So if we take the second example, the same thing is taking place in the second example as well. Let me draw that. So again we'll do the same thing, convert it to a list, and we'll have something which looks like this: 1 1 and 0 at the 0th index, first index and second index. At the 0 index we see a ball is already there, so effectively we are gonna move just 1 ball here. So this is 1 unit of work, so 1 unit. For this one we see again a ball is already there. A movement will be required from the left because we have a ball on the left, no balls on the right, so 1 unit. For the last index we see 2 balls on the left, so this goes 1 unit, and this from here to here goes to 2 unit, 1 and 2, so 3. That is why we have 1 1 3 as the answer. So this is how the solution is going to work. This is what they want us to do. Now how to do it? So for this, if we go on with the naive approach, which will be for each index we calculate the distance, keep on adding, calculate the distance, keep on adding, which we were actually doing in this approach, is not an efficient solution, and this is basically a big O of n square. So how to optimize this? To optimize this, what if there was a way wherein at each index we basically need to get what operations we are doing at each index. So let's say I'm going to take the first example again. We have this right here, right? So far we have been doing the calculation manual, like we were calculating, all right, how many times we have to move. What if there was a way via which at each index we knew exactly? Imagine these balls at each index, right? We have a thread connecting all these balls. So let's say at index 1 we have a green thread connecting all these balls here, and at index 0 we have this thread connecting all these balls here. This diagram might get messy, but this is the idea that the solution is having. And for index this one we have this position is holding on to these balls via a thread, and for this index again we are having balls connected by this thread, and for the last one, second last, again these two balls connected, and for the last one these two balls connected, 1 2. So if you see, right, what the solution, basically what we did was the amount of total pulls we are doing. So a 2 unit move, this unit move, and then again this unit is what the answer is for this index. Same goes for this. The amount of thread pulling which we are doing, the distance of the pull which we are doing, is what the answer is. So what if you take a look, take a look at this example. It says that we have to pull a unit of 1 and 2 from the right, and then 1 from the left. This is what this basically means. In all these cases, since it's a 0, we didn't have to pull any balls from the left hand side because there weren't any. But in this case there is. So what if we had an array which already told us how much pull we'll have to do for each index from the right hand side. So initially when we are here, if we knew that if we are at this index, how much pull we have to do. So let's say let me draw this again and show you what I mean. So we have this array again, right? We have this array again. Let me draw it again here. Zero, 0, 1, 0, 1 and 1. Now what if we knew at this index, when we are at this index, we'll start with the value, alright, I'm at this index, I know how much I need to pull, because this is what we can find in a single iteration. How we can find? By just iterating it. So we'll iterate 0, 1, 2, 3, 4, 5, right? So in the first iteration we know the first index that we find a single ball is what the distance is gonna be, the distance that we're gonna pull. So it's gonna be 2. Then again we keep on iterating, we find at index 4. So index 4 is what we're gonna pull. Then again we go forward, index 5. So total of 5 plus 4, 9 plus 2, 11. 11 is what we are pulling. So at index 0 we already know this is what we need to pull. This we can calculate easily. We know this is gonna be 11. Now going forward, right, we know that there's an imaginary string connecting these balls right here. Now the moment we move one index forward, move one index forward, why are we again calculating how much we're gonna pull? Didn't we just noted that we came one unit distance closer to all these distances? We came 1 unit closer to all of these distances. Now we already know the sum of it, which is 11 right here. We need to use this sum and calculate how much it's going to take us from here. So basically we're going to reduce 1, 2, 3. How we know we are reducing 3? Because there are 3 balls here. Since there are 3 balls here, we have to minus 3 from this unit, from this value right here. So that is why we had 8 in the solution set. Now keep in mind, this is only what we need to pull from the right hand side. We won't be calculating, they will be at this index, we'll have the situation where we will have to calculate the left as well. We'll do it in a separate way. Right now we are only bothered how much we have to pull from the right. If there is any ball on the right hand side, how much we'll have to pull. Alright, so let's next move forward on the next ball. So we see our ball is already here. Since a ball is already here, our effort is going to be minimized. So initially if we were at 11, right? Then we came at 8 because we came 1 unit closer. Now we are at 1 again, so it means a ball is already there. Our effort is gonna go down by 1, so we will work with a 7 here. And then again, how many balls we're gonna pull? We're gonna effectively pull 2 balls because 1 is already here. So we will maintain a counter of the ball, and then the moment we encounter a 1, we'll have to change back to 1. So now we basically are you could say 2 units closer to these remaining balls. So that is why we have to subtract 2, not 3, because 1 is already here. So 7 minus 2, which gives us 5. Now we are working with 5 here. Now we move on to the next index. Since it's a 0, so we'll still be working with a 5. It had been a 1, we'll reduce this 5 further down to 4. Now we are at 5. The effective ball count is how much? 2. So we get a 3 here. 5 minus 2, 3. I'm keeping an account of this array. We have 11, 8. This is all the pull we need to do from the right hand side. 7 minus 2, we had a 5. And 5 minus 2, we had a 3 up till this index. Then again at this index we are at 3, we encountered a 1, so 3 minus 1 becomes 2, and the effective ball count now becomes 1. Now we have to calculate the difference. 2 minus 1 becomes 1. Now we are working with 1. We move to the next one. So since one here again, this value gets reduced by 1, it becomes 0. Count also gets reduced by 1. The effective ball left is now 0. 0 minus 0 is 0. Now if you look at this array is nothing but the amount of pulls we're going to need to do to pull all the balls for each index from the right. So from this index, pulling all the balls from the right is going to take us 11 units, 11 pulls. We saw that. From this index is going to take us 8 pulls. We just calculated this. From this index is going to take us 5 pulls. How? 1, 2, and then 1, 2, 3, a total of 5. This is how the maths is working. For this index where we got 3, you see a pull of 1 and then a pull of 2. We are not bothering about the left part, we'll do it later. We'll do the same iteration from the right hand side. Right now we are doing it from the left hand side. This count here, and this is again at the same place, so it's not gonna be much. So as I said again, we just iterate it. Every time every index we see a 1, we're gonna add that to our value. So we have first we saw 1 at index 0, we add that. Second we find that index 1, we add that. Then again we find that index 0, 1, 2, 3, so we add that as well. 3. So we are starting with 4. At this point of time we are starting with 4. We're gonna have to do total of 4 operation, which is basically 1 unit here and 1, 2, 3. 1, 2, 3, 4 total operations. Now we move one step forward here. What did we discuss? If we move one step forward and we encounter a 1, there are 2 steps we're going to do. First, our effort will go down because already there's a 1 present here. Also we need to make sure that the effective count of 1 is also maintained. Initially, before we started anything, the effective count of 1 was 3. Moment we came to this index, we calculated we need 4. The effective count of 1 will now reduce from 3 to 2. Keep this in mind, since this is already in place. So at this point, moving at the second index from this side, we are working with the effort as 4 and effective count of 1s as 2s. Since we notice another 1 here, the effective effort will reduce from 4 to 3, and the effective count of 1 will reduce from 2 to 1, because this is again in its place. And then we will do the subtraction. 3 minus 1, 2. Now the effective count of 1 is 1. So now we again move to the second index. We are at 0. So again the same thing is going to happen. We are going to subtract 2 with 1. So 2 minus 1, 1. Why so? Because again, if you see, we only have to make one movement here, so that's why we get 1. So now our effective count is 1, and for this one is 2, because again 1 and then 1 again, 2. That's why we got 2 at this index, 4 at this index, 2 at this index, 1 at this index. At this point of time, our effective count of 1 is still 1 and our effort is at 1. We come to this side. Now again, since we are approaching 1, our effort should reduce by 1. 1 will reduce to 0. Effective count of 1 is also reduced by 1. 0. 0 minus 0 is 0. So at this point, we are going to have to make 0 efforts to move because it's already there. Now the effective count of zeros is 0. Effective count of 1 is 0. All of 1s are already dealt with. We are just left with zeros. We move to the next index. It's going to be 0 minus 0. 0. 0 minus 0. 0. So what are we left with? We are left with an array like this. 0, 0, 0, 1, 2, 4. Now let us take a look at both the arrays we got. Okay, I'll draw this. I'm going to remove this diagram now, and I'll take a look, and I'm going to draw 3 arrays. First array is going to be the original array, right? First array is going to be the original array. What was it? Okay, yeah, it's 0 right here, 0, 1, 0, 1 and 1. This is the effective array. This is what we need from the left hand side movement. Keep moving all these balls to the left hand side. The effort required for this index: 8, 11, 8, 5, 3, 1 0, and for this index it's going to be this one 0 0 1 2 4. Now listen carefully what I'm saying, because this is right here is what we found, and it's going to help us to find the final answer. What is the final answer? Let me also draw that. Did you notice something? If you notice carefully, the final answer is nothing but the sum of all these corresponding values. Corresponding values sum is what the final answer is. Now how it's working, let me explain it to you. So you see we got this as the final answer, but let us now look at the array that we have. So what this array indicates? This array indicates the effort is going to take to move all these balls to the left hand side for each index, but only towards the left, for each index towards the left. So for moving all these balls towards the 0th index right here, it's going to take 11 units of effort. To move up till here, to move all these balls up till here, it's going to take 8 units of effort. To move all these balls up till here is going to take 5 units of effort. Why? 3 units here, sorry, 2 units here, 3 units here. This ball is already there, so it doesn't matter. 3 plus 2 5. Similarly for this one is 3 units to move. 1 unit, 2 unit, 2 plus 1 3. Now for this unit again 1 unit, and this again 0, because it doesn't matter. Now coming from this side, how much effort is going to take to move all these balls towards the right? This is already there. We already discussed this in the previous diagram. 1 unit here, 3 unit here, 4. That's how we got 4. For this index, 1, it's already there. 2 units here, so 2 units. This side 1 unit, 1 is already there. 0 unit, 0 unit. So now if we take a look, what we are actually doing here, what we are actually doing is for each index we have find out now that the effort is going to take to move the balls all the way at this index. What this 5 basically tells us, that for these two balls to move it to this side is going to take 5, and what does it take, what does this value show here, that to move all the balls from here to this side is going to take 1. If we add these, wouldn't that be the actual work that we'll have to do? That is why we are adding. You see, it was 3 here, right? 3 here, 1 here. That is why we are adding. This basically suggests that at this index we'll have to move to all the balls remaining on the right hand side to move it to the left hand side. Basically at this index is going to take us 3 units of work. All the balls from the left hand side move it to this index, which is going to take 1 unit of work. This is what we have done. Now we have basically simplified it. Instead of O n squared, it will be a O of n. Now we have two separate arrays telling us how much effort is going to take to move the balls from left and right. At this index, if you take a look, at this index, at 0th index is going to take an effort of 3 to move the balls from right to left, and effort of 1 to move the ball from left to right. Same goes for this index. It's going to take us an effort of 8 units to move all the balls from right to left, and 0 units because there is no balls here. That's why the final answer is this. This is how the algorithm basically is working. Now we can actually to code this up, we're going to actually do exactly what we just kind of coded here, the same approach, and we'll move on now to the coding part from the left hand side. As I said, in the first iteration we directly calculated the 11 that we got using the first we iterated. Every time we encounter a 1, that index will be added. So that's what we'll be starting with. As we go forward, we'll reduce that and do the calculations that we just discussed. So for that, the left count, we'll start with the left hand side first. Alright. The list 1 r is equal to 1, right? In that case, will the left count gets increased by 1, right? Now we have the count. Now we need to find the other values. So we start by iterating list 1 again, and we'll update count then and there. Alright, so also we need one more variable which will be having the count of ones. We also need a count for that. One count is equal to This is also crucial. So now we start iterating, right? Now we are going to create this left list that we discussed. This list we are going to create for the left hand side. So first, basically, if r is 0, we are just going to append left count, because at the 0th index, be it the left side or the right hand side, it's going to be that value. So that's there. Everything after that is where now also everywhere after that there are two conditions we need to check: if we encounter a 1 or if we don't encounter a 1. If we encounter an 1, there's one step we need to do. If list 1 are, if we encounter a 1, right, what we need to do first, we need to do this 1 count has to be reduced by 1, right, and left count is also supposed to be decreased by 1, because our effort will decrease, as I mentioned there, right. Now the effective value that we are gonna append is left count will become left count minus 1 count, and then we append this to our left. If that's not the case, it's simple. If that's not the case, then left count is left count minus whatever count we have for 1 as of now, which we encountered, and then again left dot append left count. If I print this left right here, right, you can see that it is the same array that we found here, 11 8 5 3 1 0. Let's do this, running it. Right, seems like I made an error somewhere. Yeah, again, we don't have to add 1, we have to add r. Have to add an index to that. That's how we'll get the actual count, actual movement that we need to do, which is the index, not 1. I'll run it again. See, you see right here, 11 8 5 3 1 0. 11 8 5 3 1 0 is what we have here, 11 8 5 3 1 0. Now we need to do the same operation from the right hand side, same operation, but from the right hand side. So basically this list, iterating it, instead of iterating it from here, we're gonna iterate it from here. So why not quickly reverse the list, right? To do that, list 2 will be list 1 but reversed. We'll also need exactly what we did here. We'll also need a right count. Now this time we're going to need a right count. So again we iterate this, len of list 2. If list 2 r, if you encounter a 1, so the right count gets increased by 1 by r, because that's what the effort is, and the 1 count will have to be updated. So I'm going to use this variable again and redeclare it here, right. Now we have this. Now we are basically ready to iterate. Remember, we are iterating it from the right hand side now. Same concept is going to happen, same. Now we'll be getting this second part of the list. So again, since at the 0th index, right, we have to update the actual value that we have got, the left count, and then slowly this will get operated, this will get reduced. So if r is equal to 0, right, that's the first step. We simply need to append whatever value for right count we have so far, right, that we did for the left count we did. Else, if that's not the case, right, there are two conditions. First, we either encounter a 1, exactly how we did. See, it's the same process, right? Exactly how we did for the left hand side, we were doing it for the left hand side. Also it's going to be list 2 here. We are operating with list 2. So if we encounter a 1, right, else first part, if we encounter a 1, what's going to happen? First is the 1 count is to be decreased. Encountered a 1 count is to be decreased. Also our effort will also be decreased, because if we encounter 1 here, it means it's already there. So now the new write count becomes write count minus 1 count. Right, we have this. Or if that's not the case, then it's simply write count minus 1 count. And either ways we are gonna have to append that to the right list that we have. This is getting updated with each iteration. So now if I again print left and right, you will see what it is. The left and the right. We run this. Alright, again seems like some error I've made. Let's quickly see what that is. So first one is correct, 11.853.104, but on the right hand side, let's see. So list 2 is a reverse of list 1, and if we encounter an 1, we are adding the right count. Okay, it has to be right. Yeah, right dot append. Otherwise, if we didn't do this, everything else will just go wrong. So this part is like crucial. So now it's appended. I think now we should get the right values. Let's run it. We forgot about one major issue in our code. What if after appending like this, right, at this point, if our after appending at the left count is already there, it's fine. But what if at this index we encountered a 1? What about that? We didn't check that. So this is something which is gonna give us an error. It didn't happen on this side because this side there wasn't any, but because on the right side we'll face. So if that happens, we'll have to make sure we do that, right? So to quickly do that, if list 1r, which is 0 in this case, is equal to a 1, we'll have to reduce the 1 count by 1. Same thing will happen here as well, the right hand side. Now we should get the actual arrays. Yeah, 42100. If we just have to reverse it, 00124. Because remember, we reverse the original array, so this has to be reversed as well, because that's how the addition will be done. So now we just need to add these values 11, 8, 5, 4, 3 and 4. 11, 8, 5, 4, 3 and 4. That's how we are getting it. So to do that, we quickly use Python comprehensions here. Plus J. Remove this. And this should give us our answer. Yeah, it's satisfying both the test cases. I want you to try run the second test case and see it for yourself. The first test case, it's satisfying properly, and now let's submit it. Yeah, 60 minutes. That's how the solution is working. And thanks for watching. Like and subscribe.